Yeah, so can I just start?
Sure.
Okay. For this presentation, we're talking about memory evolutive systems. There's a book, obviously, written by a mathematician and a physician, I believe. And we're only going to cover the parts A and B of the book. I don't expect that any of you have read the whole book yet. But I'm just going to go through it kind of at a very high level. And if we have questions, we can dive into either the text or if I remember, because there's so many like little technical details that they go into in the book that aren't necessarily important to what we're doing at STP, right? Which is trying to model or find ways to model political action, to understand how politics can kind of play a greater role in, or how these ideas we've been working on can play a bigger role in politics. So yeah, I won't go into super high detail, and hopefully the time I spent making these pictures will make up for the lack of technical detail and make the whole thing more interesting. Yeah, so let's the next slide. Okay, so I thought it would be good to start with another plea for why we should use formal tools like category theory. Like, what's the point of it? I feel compelled to make that argument again and again because it can seem very detached from the other things we talk about, and it's really hard, honestly, to learn it really well, right? I mean, obviously, you can give the definitions for a category and you can talk about functors to people, but it doesn't really sink in just by looking at the definition, as with most mathematical things. You really have to use it a lot, see it in different contexts, and that's a lot of work. So why do we need to do that? I think it goes back to the discussion we had with Rodrigo Nunes in the last meeting, where one of the themes, the question I asked, what I was translating Raphael's question about whether he thought the relationship between like natural systems, like ecological systems in nature, and this political ecological point of view, whether that was a metaphor or something more than a metaphor, right? And Rodrigo Nunes is, very adamant that he doesn't think of it as a metaphor. He thinks this is a literal point of view that it's political at its core, and not something simply borrowed from nature. And so I think I agree with him. I think we all basically agree, because that's the main originality of his work and what has kind of been compelling for us when we talk about it. But the question is, like, what is the basis of this statement? Like, why can you say that this is more than a metaphor? What does it mean for it to be more than a metaphor? And I think that's where formal tools come into play, because as I wrote here, when two things kind of share the same shape, there's a way to characterize or capture that. The same shape is something in a logical register, right? They share the same logic. They share some kind of inferential content that you can transport from one to the other and transport back and get something new. So that's what modeling relations kind of capture. And this is an idea that is very old. I mean, as old as category theory, and obviously before category theory, there were different formulations of this. But specifically, I want to focus on this diagram that Robert Rosen puts forward in his work on theoretical biology. where he talks about formal systems encoding and decoding things from natural systems, right? So like, what is the basis of science, mathematical science, like physics and so on? It's the idea that you can take aspects of nature, turn them into equations or formal ideas. You can infer things with these formal tools, or these formal systems, and then decode it back into prediction about nature, right? And this basically this back and forth between formal systems and natural systems can be modeled with category theory. It's what is known as a functor, right? You can take and it's not just between natural and formal systems. You can do two formal systems as well, which is what category theory was invented for. Algebra and topology is an example. Those are two different parts of mathematics. You can transport information about a topological space into the language of algebraic invariance. And really, that's the only way you can study certain spaces. And then you take those inferences and you can then project that back into topology and actually create new spaces, right, by tweaking the invariance. So formal systems can model other formal systems. Formal systems can model natural systems as well. And with this work that I'm presenting here, we want to take formal systems and model social systems as well, right? So you have nature, formal systems, and social systems. All three of them have some interrelationship using patterns. Okay, so in this book, they have a concrete definition of what patterns are. Patterns are graphs, essentially. And when you have a pattern, you basically are trying to describe some very abstract set of connections between nodes and between nodes in a system. So this can be informational. This can be some other type of relationship like kinship relations, or if we're going economic, in the economic sense, it can be exchange relations. And again, the reason we're doing this is because we want to start with the basis that's common to all the systems we're trying to analyze, right? Patterns exist in nature, they exist in social systems, they exist in mathematics. So we need a very abstract set of tools because we want to be able to study this content. So a pattern consists of two parts. One is its sketch, which is just a directed graph. Here, I was really happy to see that they started from this point because it's exactly where we were going a few meetings ago with Renzo's presentation. He put forward this very interactionist modeling of society, and it had direct application to a movement in Brazil. And there was already like something very down to earth about using graphs to model things, right? And obviously there's like network theory and all this other stuff that people have been working on for a long time. So graphs make sense as a kind of a starting point for capturing patterns. What the memory evolutive system perspective offers us is taking those graphs and embedding them within categories, and allowing us to use the language of categories to describe basically patterns changing over time. So I'll get to that later on in the presentation. But basically, at this point, we just need to remember that patterns have two parts to them. There are sketches, which are graphs, and implementations, which are this graph projected into a specific category, right? And you see in this diagram, the red arrows are the arrows that came from the graph, right? The sketch here. And then the difference between a category and a graph is that in a category, you have a transitive closure, right? So if there's an arrow from A to B and an arrow from B to C, then you must have an arrow from A to C as well. And this transitive closure does not apply to graphs in general, right? But in categories, you just have way more arrows because everything's you have to draw this transitive arrows. Okay, so now that we understand kind of what a pattern is, things get a bit more interesting because we can start to talk about objects that are privileged with respect to a given pattern. So before we go into that, we can talk about objects that are within a pattern, right? The objects within a pattern are connected by something called distinguished links. So we took something like a sketch, right, which is a really abstract idea. We project that into a given situation. For example, workers and machines in a factory. So this sketch now is incarnated in the form of different individuals interacting with machines, producing things, exchanging information. This is happening through the distinguished links of the pattern, which are colored red in this diagram here. But we can now, once we've implemented the pattern, we can now find specific objects that relate to all of the objects within the implementation. These are called cones. So this purple dot here at the top is a cone with respect to a pattern. And the reason we can say that, for the formal reason, is because every arrow, every green arrow here can be formulated as the composition of a red and a green arrow, right? So H is equal to G and then F, right? If you follow G and F, you get H. And the same for the other ones as well. Like if you were to label these other ones, you could do the same thing, right? And any triangle you form, you will have an equivalence. So these green arrows are called the collective links. And what they capture is what of this pattern is operating together in unison or towards some common purpose. So in the example of a factory, you may have a manager that is coordinating the work of all the workers and the machines together, right? This doesn't mean that the manager somehow captures everything about the pattern, right? The pattern can be, let's say, having information that is not preserved in the composition. But what this is saying is that anything else that wants to interact with this pattern can just as well go through its cone. Okay, so there's something about the cone. Something about the cone summarizes the standpoint of this pattern.
Okay. I didn't understand if the cone is, you have a cone for every implementation of a sketch, or is it just a particular kind of structure?
Yeah, it's a good question. So yeah, the answer is there does not necessarily need to be a cone. There can be patterns without cones. So it is contingent, right? For the given category that you're working with, you may find patterns that don't have cones.
Mm-hmm.
Yeah. And yeah, similarly in a factory setting, you may have workers that don't need a manager. They operate autonomously, and with a flat structure, for example, and that this formalism doesn't make any assumptions about that. Okay, so
let me just ask another question. So you have a cone when you have something that can connect in the way you showed with all the elements of the pattern. Like, for example, if you have a manager, to take your example. So it's something that it's not it's something that is in the same level of the other nodes. It's not a meta structure, for example.
Yeah, not necessarily. So later, I will talk about something that is like a metastructure. There's a way we can model hierarchy in such systems, but hierarchies are not they're not a necessary property of categories. So it's both, right? You can do this object can be one of the objects in the pattern, actually. It doesn't necessarily need to be an object outside of the pattern. Right. So all that's required is that this object has a set of arrows that obey this property that is drawn here, that they basically commute with all paths. So if any path you take to the cone is equivalent, basically. So if I take G and F, it's the same as if I took H. That's the only condition it requires, and so there's no need for hierarchy in this description.
Okay, so and these are the collective links.
Yeah, the green ones are the collective links. Yeah.
Okay, so if you have collective links, you will have which is that situation where all the paths are the same. You will have a node, a cone. Sorry.
A cone. Yeah.
Okay, thanks.
And I think you might have already said it, but so the target, it may not be part of the original sketch, right? It can be.
Yeah, it can be inside or outside. It can be outside. Yeah.
Okay. Is there like an interpretation of when it's already part of the sketch or not, or only part of the category, or doesn't matter that much?
Yeah, it can be for formal reasons, like in a partially ordered set. Every set of nodes in there automatically has a least upper bound. So for formal reasons, a sketch that has an implementation in a partially ordered set will always have a cone, right? It really depends on the structure of the category in which you're mapping to. Some categories may look like a tree, right? If that category looks like a tree in which any set of elements has an element that is greater than it, or somehow like sits above it in some sense, then you basically have a hierarchy built into this category. But sketches are not necessarily, they're independent of the category, right? They can be mapped to different categories. So I can take the same sketch and map it to a hierarchical category, in which case I'm guaranteed to have a cone. But then I may take the same sketch and map it to a non-hierarchical category or some other kind of category, and there I don't have a cone. So it really depends on the category, which is the space where this sketch is being implemented. And I think a good interpretation of this would be like, the thing we've been talking about, which is, taking ideas from different political movements and trying to apply them in different places, right? why is it that some strategies work in some places but not in others, right? There's some intuitive sense of like the conditions for applying certain strategies determines how successful that strategy will be, right? And these conditions are kind of this vague thing, right? You don't really know what they are, and in general, you don't know why some things work in some place but not in other places. I think that's kind of where we could start to analyze that using this, right? Why is it that in some cases there arises a leader that can unify a movement and make that movement more effective? In other places, no leader arises, and maybe it succeeds still. It still does makes progress, or maybe it stalls in that. And a leader doesn't necessarily need to be an individual, right? Since these are very abstract, sketches are very abstract and categories are very abstract, these can just be functions as well, in the sense of not in the mathematical sense, but in the sense of like a political function. Yeah, but I'm gonna go on, and maybe we can come back to this, and I think it'll make more sense. So here's the first concrete example. Somewhat concrete. So a pattern doesn't need to have only one cone. A pattern can actually have multiple cones. An example of this would be in a city. So imagine you have a city and you have different neighborhoods, which are the different shaded regions of the city. And then you have roads that go through the neighborhoods, and you have train stations. Okay, you have 3 train stations here. And because all of the roads allow one to travel from one neighborhood to any of the train stations, we say that these train stations are cones, right? This is ignoring like the cost of transportation or how convenient it is, but just considering like connectedness. Train stations are accessible by any neighborhood here, right? And the roads you would take to get to the train station correspond to the collective links, right? So you can imagine like from this gray shaded neighborhood, if I wanted to go to this the bottom train station here, there's some set of roads I need to take to get to that. That would be a collective link, right? And then for any of these neighborhoods, you would have a path to any of these train stations. Now I'm kind of cheating here because I said earlier there's this property of the collective links, which is that any path you take must be equivalent. So if I take 2 different paths from the same neighborhood to that train station, they should be the same. But honestly, there's obviously there's like a shortest path here, and that's the path you most likely would take. But assuming like cost was ignored, for the sake of this, for the sake of the example, we can say that if this property is already satisfied, right? If it's accessible. Okay. Now, when we have this situation of multiple cones, we can start to talk about the operating field of a pattern. So this pattern has for this operating field, each cone forms an object. So it's basically another category that you can form from the original one. And this represents the kind of the scope of activity, right? How wide of let's say in this case, how reachable is this pattern, right? Again, the pattern here is the neighborhoods themselves and the roads between them. And the operating field would be something like this, an abstract representation of how reachable things are. And the point of all this is to say, like, if you know the train stations, you kind of know the neighborhoods, right? If you know the train stations, you basically understand how to get around in this neighborhood. So if someone comes to the city, you don't need to describe every single road and every path. You just need to tell them, just go to the nearest train station, and using that, you can get anywhere in the city. That's kind of the intuition of this, right? The operating field is kind of like a summary of the pattern from the standpoint of its cones. And it's formalized by, it's a category, which in this case has 3 objects, right? Each object is one of the cones. And you have these white lines, which are the paths between train stations. So if you know the path, if you know the train stations and you know the paths between them, you know the operating field of the pattern.
So the operating field is already a sort of abstraction over the original sketch you had, right? So you first like have a sketch and then it sort of collects cones. Like say you have a factory and then you have different managers that they manage over particular sectors of a factory.
Mm-hmm.
So this operating field is described by the way that the managers that the category of these managers, which are cones that look at these workers, would be the operating field of the factory.
Exactly.
Okay.
So if I were to come to the factory and say, you know, what is the status of this factory? I don't need to speak to every single worker. I can just talk to the 3 managers, or I can sit in a meeting and watch the 3 managers interact. And by seeing how they interact, I know, okay, this factory is doing well, or, oh no, this factory is dysfunctional because I see one of the managers is always arguing with the other 2 or something like that. Right. There's, like you said, it's a layer of abstraction that
and it's the name of a perfect abstraction, like it's a perfect reduction, or is it just a reduction in general? Like it could be a bad abstraction.
Yeah, it could be a bad one. It only needs to satisfy this idea that, like, the information. So, okay, let's look closely at this example again. Let's say the arrow G is the interaction between 2 workers, and there's a lot of information there, right? Because these 2 workers know each other outside of work. They've worked together for a long time, and there's a lot of context in how they interact. Now, one of those workers, actually both of these workers, report to the same boss, which is the purple dot. Some information can be lost in the passage from G to F, right? So if you have some interaction G, and then you have another interaction F, the interaction F may be very, because, you know, maybe this worker doesn't have a great relationship to this boss. So yeah, like you were saying, it's not a perfect abstraction, right? And the only rule is that if this worker has a kind of shitty relationship to their boss and they lose a lot of information in the arrow F, it must still be enough information to capture the relationship between the first worker and the boss, which is captured in arrow H, right? So the formula H equals G and then F, it's the constraint on how bad the abstraction is, right? The abstraction can be bad, it can be very poor, but it has to be somehow equally poor. If F is poor, then H must also be poor, right? It cannot be that H is, let's say, a very rich relationship between the worker and the boss, and F is a poor one. They They must somehow be compatible. If that makes sense. I'm seeing there's a lot of messages and yeah, are there any other questions here?
Did what we say here in the chat make sense then?
There are also roads to train stations such that any two paths to the train station get you to the same place. Yeah, that would be the same condition, right? So in the context of traveling, you don't care how long it takes or how much it costs. You just want to get there. In that sense, yeah, taking two roads and a train is the same as taking another train, right? As long as they get you to the same place.
Dennis, would it be fair to say that the step from like the sketch and the graph to like the equal sign is like, because I know Rosen talks a lot about the link between semantics and questions, right? Like it really depends on what you're asking.
Yes.
Whatever lays behind. Like if you're asking, can I get to a place? All those become equivalent and it becomes a cone. If I'm asking, are they all equally time consuming or gas consuming? It might break it as a cone because they're not equal, they're not equivalent.
Yes.
If I'm asking like, I don't care if it is like more or less 15 minutes difference, then some of them may be equivalent and others won't, right? Like, so it does kind of depend on what you're asking of the information that depends on how you actually decide what is or is not equal.
Yeah, that's a great way to put it. For someone who needs to save money, a small difference of a 15-minute fare or having to make the a slight detour to get to your final location, that's going to be a deal breaker. And therefore for them there is no such like the operating field is a lot less, right? It's poorer. Yeah, but for someone who's rich, has plenty of time, it doesn't matter, they can kind of start from anywhere and go anywhere, and it really doesn't affect them, right? They have time to spend. They don't need to get to work at a certain time. They can just they're just kind of wandering the city. Then yeah, from that perspective, you have more cones.
So is there a term, I guess, for something like whatever's below the operating field from which you're kind of extracting information in this?
Yeah, it's the pattern, right?
Wait, so like the total city would be the pattern? Like if you're looking at the city?
Yeah, so again, it depends. So in this case, the pattern are the neighborhoods, and the links between the distinguished links are the roads between neighborhoods.
Okay.
So you have what are the parts? You have distinguished links, which are part of the pattern, and then you have collective links, which go to the cones, and you have the operating field, which abstracts away the underlying pattern and only talks about the cones themselves and their interactions.
I have a stupid question about the diagram, the drawing. If we are talking about collective links, shouldn't the train station in the middle, the one in the green zone, shouldn't it be connected to roads? Because since those are the distinguished links.
Yeah, that's just my bad drawing. Yeah,
no, okay, just because I was wondering if it was some conceptual difference that escaped me, or if, but okay, because it seemed like, oh, there's this cone that's different, and I was thinking if there was something that I was missing, but thanks.
Yeah, I mean, I think, yeah, in some examples that, you could say, I could take a road and then take a train to get to the bottom, that middle one. And therefore there is a path there. But it would not be a distinguished link. It would be a composite of a distinguished link and then a composite link, a collective link, right? Since the white lines are the collective links. So we're saying here that there must be a distinguished link to the cone. Yeah, let me think about that. Does that need to be true? Because in this case, if the red arrows are the roads here, there's no red arrow to the purple purple dot here, right? So yeah, it's not the case that it always has to be a road. In this case, there's not one.
Yeah, but isn't there, perhaps just making the distinction between, there must be actual links, they might just not be distinctive links of the pattern, right? So if the pattern is roads connecting neighborhoods, the roads that actually connect to train stations might not be in that pattern because they're not distinguished for that pattern, but they must exist.
They don't need to exist.
Because there is not a qualitative distinction between the collective links and other links. Like they're all.
Oh, yes. Actually, no, you're right. You're right. Sorry. I was saying that the white links were the collective links. That's not true. The white links are the interactions between the cones. They're the link. So links between cones are not the same as collective links. Collective links have to be going from, in this case, the neighborhoods to the cone.
If you can just go back to the previous slide, I think it's helpful.
Yeah.
Like actually, first of all, you should just think of all the arrows here. They're all connectives, right? All links in
Roads.
general.
Yeah.
They're all roads. It's just that the red ones are the ones that matter if you're concerned with connecting neighborhoods. So that they're distinguished or relevant for the pattern. Right? I mean, taking you to a train station doesn't necessarily mean that it's taking you to a different neighborhood, right? So you only distinguish these links. So they might be distinguished for the pattern of connecting neighborhoods, but they might not. And that's going to tell us if these links are part of the pattern or not. But they're also roads. What qualifies them as collective links is that regardless of whether they are inside or not the pattern, they have the property of creating these cones.
Exactly.
Right.
It's a functional definition because, yeah, materially they're all roads, but some of them are distinguished, right? Because
like imagine here are the neighborhoods, right? Like,
yeah, exactly.
So it might be the case that this is like this inside the same neighborhood. So for the pattern of connecting neighborhoods, this is not a distinguished link. But because it satisfies that other property, it becomes a collective link, right?
Exactly. And yeah, it's collective in the sense that it kind of binds all the neighborhoods, right? In some sense, right? It's kind of the same, the equalizer between all of the neighborhoods, because all the neighborhoods, you can take a train, basically. Another thing that's a bit unique about the example with the roads is that roads are two-way. The arrows here are one-way, right? If you have two arrows, if you have an arrow going back and forth, then you have kind of a two-way connection, but that's not required. So the direction matters in general.
I'm just going to insist on this because I'm sorry for slowing things down. It's because I'm not understanding. I'm not getting quite how clear. I'm not getting so clearly. In what sense are the train stations nodes in this example? They are nodes due to the fact that when you consider any path on the roads, I mean, because from the like it's from the other example, it was something like, well, you have this, you have different points in a pattern, and then if you go to the node, it's the same path as going through, like going from G to H, it's the same as if going H is the same as going GF, right? That's the property that is true.
Yes.
For when we have a pattern, for when we have a node, a cone. Sorry, mixing all the terms. I'm not understanding in how this in the train station example, how this is made true. I mean, what are the, I mean, if you could give an example of what would be the like H and what would be the GF that are the same. And I know that you said not considering distance, time, cost, or whatever, just the same and last point. I mean, that's not what I think it's not so clear to me, because I can understand abstractly. I think the manager example worked a bit for me for understanding, but I didn't get it in the road one.
Yeah.
Okay.
Yeah, good question. So imagine that to every arrow we assigned a true or false. True meaning it is accessible, and false meaning it is not accessible, right? And in that case, when we take two arrows and we compose them together, we basically do a Boolean, right? How do I say it? Like if two arrows are true, then their composite must be true, right? So G is true. Let's say G is true, F is true. GF then is true, right? Yeah, if I can access the first blue dot to the second blue dot, and then the second blue dot to the purple dot, then the whole thing is true. And that is exactly what we would assign H as well. H would also be true. So then you have true equals true in this formula.
But I think his question is just that, I mean, to turn that other example into this graph, just imagine you have another cone, so another station with roads leading up to it. And you were asking how do you understand the connection between stations, which is a railroad, right?
Mm-hmm.
So here it is. Like, imagine you now have other roads taking to a different train station, which also works as a cone. So it has the collective link. So if you compose these arrows together, you get the same type of property, right? And the train stations are now arrows between cones, right? It takes you from station to station.
Mm-hmm. Yeah, exactly.
Right. And if you go from one station to station, it's like all these things now are mapped back onto the other ones, right?
Yeah, and you'll see that the formal constraint that I just said, it also applies to this. If it's true that you can get to the first station, then it is true that you can get to the second station because of the rail, right? So when we say forget about cost and forget about distance, I think we're reducing the content. The content of the arrows is just the logical assertion of whether it is reachable or not. Can I get there? But
okay,
the example in the book actually makes more constraints. I didn't use it because it's a little more complicated, but imagine you have a number to every arrow and the number tells you the cost. Then it's not as easy to work out what is a cone and what's not a cone, right? Because if the costs don't match up, if the cost of H is not the same as cost of G then F, then this example doesn't work. So you have to assign the numbers in such a way that it starts to work again.
But did it make sense, man? What are the railroads would connect would appear in this other version of the diagram?
Yeah, what you said makes total sense. Yeah.
Yeah, but just for Rafael who asked the question.
Yeah, I think that part made sense. I'm just going to ask another thing because I'm sorry because it's all very abstract for me. But we are considering for the purposes of this neighborhood connecting stuff that the connections are like, if you have a path that you have to take a road to arrive at some place. You can't like go off road. just so I'm going to start on a stupid level. I'm sorry, but just so I can clear my question, right? You have to take. You can't like go off road on this example.
In this example, no.
Okay, that's why I'm trying to understand. So it's like if you are like on the red, on the I mean pink, going like through the orange, and then on the gray. I mean, I'm sorry, I don't know how to name colors. It's a cone if you go to the pink and then to the dark green and then to the light green and then to the gray. Like if those things are the same, then there is a cone. Is that the or no? Because I mean that's what I'm.
Yeah, if starting from the pink, let's say you're starting from the pink, the bottom neighborhood, right? Pink neighborhood. You want to get to the pink train station at the top. Okay, you have many different paths you can take to get to that top pink station. The property says that all those paths are equivalent.
And the collective link is not like the road path. It's like the fact that all these paths are the same.
Yes.
Okay, just so okay, because I think in my mind I was confusing the things, and I'm sorry I was not getting a hold. But okay, I think now it's
no, but I think
now
this is good.
Yeah, I think this needs to be very clear. Like you can have many connections. Like this is not yet a pattern. A pattern is like it needs to be the implementation of a particular sketch. So from all the ways you can walk around between neighborhoods and paths you can take inside of neighborhoods, this particular sketch is only concerned with dots being neighborhoods and arrows being roads between neighborhoods. So everything else, all the walking around disappears and you only have that.
Yeah, sure.
Right? So all the roads connecting the neighborhoods are counted. This is, let's say, the first red arrows and dots in the first schema he wrote, right? The first diagram. Okay, but then sometimes amongst those, you'll have special kind of compositions between roads, and you might have a cone inside of the red thing. But sometimes you actually need to consider more arrows. For example, roads that are not taking you across neighborhoods. But nevertheless, those arrows, they still take you to these train stations that satisfy that property that we call the collective link. So it might be inside of the implementation of the sketch, it might be outside, but wherever it is, these extra roads, they're still roads.
So we didn't say
okay, so, they're still roads, but they will satisfy this added property. Then we'll call them collective links. The graphs, the roads that were inside the sketch, meaning the roads that connect neighborhoods, we'll call them distinguished links, right? The relevant links. So we're only inside of, still only talking about roads and places that roads connect, right? The distinction between collective links or not collective links is just if they functionally have the property of any two paths to these points, commute.
No, okay, I think I understood. I think the problem was that I was trying to fit the collective links like onto the roads, and I think that was mixing.
For example, I think if you change for the, let's say, you have a sketch of how to create a product, so it will be implemented by workers relating to each other. It might not include the manager, to which every worker has a relation. You might also have a sketch that includes the managers, like you're implementing the whole factory, right? So managers are included, but that doesn't matter. So you have the distinguished links between workers. You have connections between every worker and the manager. And let's say you have two managers because you have like quality, the manager for quality purposes, the manager for safety purposes, right? Then you can also have relations between the managers, right? Because they can talk about all the workers between the two of them, right? That's where, let's say, the railroads are coming in.
Yeah, and you can definitely imagine like not being concerned about levels below this the managers, right? Like if you're
Yeah,
higher up, generally you don't care about the bottom level workers. You want a report from the managers level.
but
And-
yeah, but at the same time, this whole structure is only valid because the same way that a quality manager sees every worker below them or get information from all of them, a worker can either go straight to the safety manager, or he can go to the quality manager. The quality manager goes to the safety manager, right? With the information.
Yes, that would be the property of this, right? The commutative property.
Yeah, but for the connections between cones, right?
Yeah. Yeah, I will say, like, just as a reminder, in a category, this property is that's just always true, right? Anytime you have two arrows, if you draw these arrows in a commutative diagram, you create this condition. That's not to say that you can't have arrows that don't obey this condition, but they just cannot be let's say pictured in a category together, unless you explicitly say like this is a non-commutative diagram. But the standard way of formulating these things, every arrow obeys this property. I don't know how useful that comment is, but okay. So we have this notion of operating field, which kind of summarizes the or abstracts the pattern. Later on, we'll see there's kind of a inverse version of this called the perception field, which is what a pattern is able to see. So you have both, right? You have both summarizing what a pattern can do, and also what a pattern can kind of absorb from the outside world. But they're both kind of summarized in this way. Okay, so we've talked about cones, and I mentioned earlier that one pattern can have multiple cones, right? So when you have that situation, there can arise a cone which is special among all the cones. One cone that is has a certain property such that all other cones are it is a factor of all the other cones. So in the example of the city, if you had a train station from which it was possible to go to any other train station, but not necessarily the reverse, right? It's not possible that all train stations go to this one, but this one can go to all the other ones. Then this train station would be a special cone among all the other cones, right? And we call such objects colimits, right? And it's not guaranteed, again, it's not guaranteed to exist. You may have a situation where you have a network of train stations, but they're not all connected. There's no one privileged train station that's like central to all the other train stations. In that case, you don't have such a colimit. But when you do, it's a special situation that this formalism is built for this type of scenario where to ask the question, do we have a colimit or not? It's a very important question, and we can apply it to all the different scenarios, like natural systems, formal systems, social systems. I wrote here an example in a social situation or political situation. If you don't have a consensus, then you don't have a colimit, right? Building a consensus is like building a colimit, and it happens step by step. It's not necessarily it just is or isn't, but maybe it's in progress, right? So maybe at a certain time you have cones in a political movement, meaning you have certain factions of the political movement that kind of summarize the movement as a whole, but you don't have a consensus. You have different factions, different tendencies that summarize the movement, but these tendencies are not all unified. Then you don't have colimit, right? Because the colimit is a special cone that serves as this factor, this kind of if we want to talk about it in formal terms, it needs to have a unique arrow to any other cone. Right, so this in this picture here, the purple is obviously the pattern, right? And the cones are the different green things. The collective links are these green things. And then you have the cones are the circles. So the co-limit is one where for any other cone, there's a unique path to that cone that respects the commutative property. So if I go from an object of the pattern to this co-limit, there's only one way I can go to another cone that respects the going straight to that cone from the pattern. Which, yeah, I mean, the fact that it's so hard to say in ordinary languages probably says something good about the formalism, maybe. It says it summarizes a lot of information, but yeah, just think about it again, going to the city example. It's a train station that is kind of special among all the train stations. And in the book, there's a whole section devoted to what they call the binding problem. There's a lot of examples they give. Some of the ones I liked, imagine you are, in the jungle, and then you're an animal, you hear a noise, and then later on you see footprints on the floor. If you're able to connect those two things and say that this is like a predator, like both the noise that you heard and the footprint on the ground, or the paw print or whatever, if you're able to connect those and say that this is a predator, then you've successfully you've solved the binding problem. But let's assume a case where it could be a predator, but it could also be just another animal, or it could be something that's just irrelevant. Actually, you have three cases. Case one, you don't see a relationship between the noise you heard and the print on the floor. Then you don't have a cone at all. There's no cone because you don't have a collective link that connects those two things. That's case one. Case two, you do see a relationship between the sound you heard and the print on the ground. So you do have a cone, but it's not necessarily the co-limit, right? Because it's not necessarily the privileged among all the possible sources of these signals. And then finally, if you realize it's a predator and you need to run away or hide, then you have a co-limit. Right. So yeah, this is
Is it a co-limit because you're reaching a definite conclusion? Is that the step?
Yeah, it's the one that maybe the predator thing is not great, but it's the one that explains all the other explanations. Yeah, I think the predator thing is actually not a great example I think it's a better one would be if you're a detective and you are investigating a case. Every cone is an explanation for the clues you found. The final let's say the smoking gun, or the definitive explanation is a co-limit.
So I don't know if this is the best way to formulate it, but is that like a qualitative or quantitative difference? And I mean that in the sense of, like, in the detective case or any kind of, I guess, investigative question, like if you're ultimately deciding amongst your hypotheses, what's the most likely, and it's not like a definitive, this is like what happened, but this is the most likely thing to happen, does that become a co-limit, or is that still just a cone?
Yeah, if it can explain all the other stories, then it's the co-limit. But yeah, I don't think it's necessarily has to do with probability or likelihood. It has more to do with the explanatory power of it, or the way, at least the way I'm thinking of it, is that the unique arrow, which is here represented by the dotted arrow here, it has to be of this kind of the same stuff as the collective links and the distinguished links, which in this case would be like explanatory or inferential content, inferencing of clues, right? So the unique arrow would be something like the one explanation, the unique explanation, such that the other explanations kind of make sense from this perspective.
Okay, so it doesn't just like have like the best explanation about like quote the object, it's like the one that also takes all the other arrows.
Yeah.
Okay, yeah,
It has to take all the other arrows into account.
Okay, so this is a very like, okay, yeah, so it's an interesting idea of entailment there then, yeah.
Mm-hmm. Yeah, it's very, I think, related to like abduction, or taking a set of possibilities and kind of narrowing them down till you get one that's in some sense better than all the other ones, or at least equivalent to the best solution. Because actually, in category theory, a co-limit doesn't have to be, it is unique in a sense, but it could be that there are several options that are unique. Several options that are equivalent, and together they are the co-limit. But that's another side comment that it's probably not useful here. Okay, and when you're planning a city, let's say if you're trying to decide like where should I put a fourth train station, you're probably solving some version of this binding problem, right? Because you're trying to find where to place it such that you can minimize some set of constraints of cost, efficiency, or whatever, right? Again, in the example we gave, we didn't care about cost, but in a more realistic example, you would be trying to solve the binding problem with respect to some cost constraints. So it's a really wide-ranging and very practical way of formulating things. Yeah, the problem is that I just couldn't find an example that was small enough that I could cover in this presentation that wouldn't take up the entire time. But yeah, I'll try to think of another one where we can actually bind some information together. Okay, so again, I was giving the example of the detective and the predator. They're all part of the same idea, which is that you have some phenomenon that can be processed by a pattern. So earlier we talked about the pattern and its operating field. So that's how the pattern interacts with the outside. But a pattern is also how you can parse things from the outside world. So each one of these purple arrows here takes some given phenomenon, which is represented by the gray ball, and each purple arrow is an aspect of this phenomenon. And the reason I chose 5, I was thinking specifically of organs, like sense organs. So you have, your taste, touch, sight, sound, and so on, right? Those would be your pattern. That would be the pattern that is able to parse some phenomenon out there, some event, let's say, that happens. You feel it, you see it, and so on, right? And then there's something that needs to happen for you to unify all these different sense representations into a unified perspective, right? And that's why I evoked Kant here, right? And this is like his territory of, there must be some transcendental conditions, and the same subject must kind of persist in time in order for you to do this operation, right, of like synthesizing some sensory thing. Okay, but we don't have to go into that. It's just that the binding problem applies to phenomenon, the phenomenological world. And the crazy thing is, this same process is the one that's happening with the city, right? So we're building a formalism that applies to detectives on a case, to people planning a city, and to like phenomenology, right? The same formalism can be applied to all of those things. Okay, so yeah, that's kind of the first few chapters of the book already. We're already pretty far into it. Now we can start to talk about the more interesting stuff. And it gets a little more, I think, practical. So patterns can be linked together. So we've already talked about how patterns can be bound together by the co-limit, or they can have cones and then an operating field. Now we're talking about 2 separate patterns and how they relate to each other. So we say that 2 patterns are connected together by a cluster, and a cluster is just a set of links that take the objects in one pattern to the objects of another pattern, such that, again, the commutative rules apply. So the same thing we saw with this H equals G then F. If we take a cluster path, so from the left orange pattern to the right orange pattern, if we go through that blue shaded region, and then we go through the green shaded region on the right hand side, it's the same as if we went to the green shaded region on the left and then took the little purple arrow to the right. That's what the property is, right? And if this is the case, then this purple arrow is called a simple link. Okay, and the meaning of simple links is that it's like the railway example that we were just talking about. Like, you kind of summarize some information between 2 clusters by just looking at a small part of it, or some other smaller entity. And you could say that a simple link is basically reducible to a cluster. It's just a very simple summary, right? Like, if you know the cluster, you know the simple link. But the simple link is just it's kind of a condensed version of it. So an example here would be, again, if there's workers between 2 departments, there are a set of workers in department 1, a set of workers in department 2. If the interests of these workers is represented by their managers, you basically only need to look at manager 1 talking to manager 2, and you can basically know everything you need to know about the underlying. Actually, it's the reverse, sorry. If you know the relationship between the workers in department 1 and the workers in department 2, you pretty much know what the manager is going to say. Right? That's a bit different. Simple links are those links that can be reduced to the underlying cluster. And if you compose 2 simple links, you can get another simple link. But in some cases, you get a complex link, and those are not reducible to the underlying cluster. They're not represented by a cluster at all, really. They're emergent. And so the whole point of this slide is just to set up the conditions for how we can talk about emergent phenomena in this system. Right? Because you may know all the relationships between 2 sets of people, but in their interaction between them, something may arise which doesn't correspond to this cluster of relationships. Right? Just like in STP, we have our own kind of personal relationships to each other. We may talk to each other outside of STP, but when we meet together, there may be something that emerges that is not reducible to the set of like personal relationships, right? So that would be an example of a complex link. Okay, and this slide is probably the most important slide of the whole presentation. It's their version of a site, I would say. You know, in Badu, there's a certain condition you have to satisfy formally in order to have an event, and events are Badu's way of modeling like radical changes in a world, like a big kind of reordering of things. They have something like that in this formalism, and it has to do with special objects that can be decomposed in 2 different ways, or 2 or more different ways. So here, what I wrote is, usually an object has only one decomposition into its underlying pattern. I think implicit in this is the idea. Previously, we were talking about how you can bind a pattern together into a single object. Well, you can also do the reverse. You can look at an object and say, what is the pattern that makes up this object? Right? You see a human individual, what makes them tick? Okay, they have a childhood that's this way, and they have these life experiences, and they're from this culture, right? You decompose that individual to their underlying patterns. This process of going in reverse is not guaranteed to yield a unique pattern, like a single pattern, right? And this makes sense, right? If you I think the whole reason why psychoanalysis exists really is if you try to decompose an individual, you don't just get one pattern, you can get multiple patterns. And the reason you can do that is because there's some kind of emergence or complexity at play in this object. This is what they call the multiplicity principle. Gabriel, do you have a question?
Yeah, no, it's one comment just to make sure. We were talking about this in the chat, and also a question. The comment is just that I find that sometimes, just for the sake of making the examples clearer, we don't respect one condition which I know it like to be very crucial to all of this, which is it was clearer in the beginning that like all of this is constructed out of the principle that we're always talking about, let's say, arrows made of the same stuff, right? I mean, in the example of roads, we were talking about roads, and I mean, perhaps that's not as general as it should be because there are railroads and roads for cars, but ultimately it's like distances between places, right? And all the properties that start distinguishing places, some are cones, some are arrows between cones, all those different properties, they're just functionally distinguished, right? They're distinctions based on the relations between let's say fundamentally homogeneous arrows, right? They're not like one arrow which is like X perceives Y, and a different arrow which is X reasons about Y. Like, I understand the example because it gives that idea of I take in a lot of different information, then I kind of synthesize it. But what might get lost when we talk about it in these terms is that it will take like, I don't know how many layers of complex construction to be able to state within this theory, I perceive something, therefore I reason something, right? Because you want to keep this idea that all the arrows that you're constructing with these patterns, and then the cones of the patterns, then the relations between cones and so on, that they're in some level made of the same thing. You don't want, let's say, to import properties that are given because you added an arrow of a different quality, right? So I know that for the sake of the example, sometimes like it's good to forego this distinction just so we can make analogies that are clearer. But the reason why the book is like so long also has to do with the fact that they need to never skip a step and never add a quality or a property that is not relationally defined rather than substantially defined, right? So I think that that's just a comment that I find that it's a good thing to keep in mind that, for example, when we talk about these distinguished links and then collective links and then operational fields and then co-limits, this is all kind of flat in the sense that we want to functionally derive like hierarchies, like positions or functions that different things might take that are heterogeneous out of a more homogeneous grammar, right?
Yeah, I see your point, and I think they take an easy way out of this problem there's a section of the book where they talk about information, and I think information is kind of a very easy way to say, you know, what connects, what is seeing and perceiving something, what does that have to do with like acting on something? They in their grammar, it's just the transfer of information. So yeah,
but then let's say even if that's the case, then all the arrows are transfer of information, and if you want to say something which is we wouldn't say in that way, you'll have to derive that property, right? Let's say we would say no, reasoning is not just transferring information. It's very complex kind of thing. Yeah, but now you're committed to deriving that complex property out of just constructing very complex compositions of passing along information, right?
Yeah, exactly.
So there is this commitment to what are the objects and what are the arrows very early on. And this is what, let's say, makes the whole game so complex in the sense of like so sophisticated and so time consuming and effort consuming. If you could just shift in the middle of it, like these arrows, they're information transfer, but this one arrow now means I'm reasoning about something. You wouldn't be playing by the rules of the game, right?
Yes.
I think it's good to have that loose kind of use of it just for the sake of passing along kind of good intuitions about what's at stake. But just for the sake of the whole group, you know, I think it's always good to come back to that version of the problems. Like, holy shit, so I need to be able to distinguish what is a central node in a network of train stations from what are just other nodes, simply based on the relations between. I cannot counterband, I don't know how to say this in English, like, you know, bring a forbidden property into the game that I, you know, that I didn't construct inside the game, right?
Yeah.
So that was the first thing. And the second thing, now it's a question, just make sure I understand, because when I read this, I always felt like the multiplicity principle is a bit tricky, though it's central. Like, in this kind of layers of restriction, right? I have just a bunch of connections amongst nodes. From them, I reduce to implementations of sketches, like patterns. So let's say I could have, does this make sense? Like I could have something like this, where this has like a bunch of arrows, but only like given a certain sketch, only some of them count as part of the pattern, right? Like this one, and this one, and this one. This is a pattern, and in this, in the same kind of environment of connections, this one, and this one here form another pattern. I don't know. This is what these two things here mean, right? That I kind of selected two patterns within the same kind of richer graph space or whatever.
Yeah, exactly.
Right. Okay.
And between any 2 points in this category, there can be many arrows.
Yeah.
Not just one, right? Yeah. So that, many different forms of relations.
So actually, like we're supposing like this fuzzy space of a bunch of infinitely many connections. Then you have, let's say, one pattern which is just selecting some of these, and another pattern which is selecting, I forgot what colors I use, just selecting some other. This is the multiplicity principle, that I could select these two patterns out of the same fuzzy realm of possible connections.
Yeah, not only that you select the 2 patterns, but that they are bound together by the same object.
Yeah, true. So there must be an object that they both have collective links to.
Yep. And that is for them complexity. And what it means is that I cannot reduce this blue line to the composition of these 2 purple lines, which are the simple links.
Okay, no, that's not complexity. That's the condition for complexity, right? Because let's say I have these 2 patterns with the same cone, the same colimit, right? And then this other cluster here relates to this cone in such a way, so there's another one here, right? That it's a simple link, right? Because what's contained in this upper arrow is the same as is contained in this lower one. And this other cone here for this cluster here is also connecting with the same pattern. Even though 2 patterns exist, it's connecting with the same. Then it's just simple, like this upper thing here will compose as a simple composition as well. Right? This arrow here needs to go to the other pattern for this to be the case, right?
Yeah. No, it's a good point.
Right, there can be multiple patterns with the same colimit, sorry, but if these 2 things are not going each to one of these 2, then the complexity, the emergence principle doesn't happen. Right? The crucial thing is that this is mapping onto one pattern and this is mapping onto another pattern. And that's why this upper arrow won't simply be the composition of the bottom 2. Yeah.
Looking at the purple arrows, looking at just the simple links, it's not enough to tell. You have to look at the cluster, the underlying clusters, right? Which again, they're the links that take one pattern to another. So yeah, you have 2 different clusters, but they don't share the common pattern in between. They do share the same colimit, and that disjunction is what leads to this
so cool
situation.
Does this make sense to everyone? Like, I think this is really the crucial.
Really crazy.
Yeah, I'd like to ask a question to see if it makes sense for me. So if there's this situation where a cone serves 2 different clusters, then you are not, there is not a simple link in the sense that you were describing, where you can simply go from one to the other, right? That's the first step.
Mhm.
You have a cone that is the cone of two different, I'm doing movements, but my camera is off. But it's like, just like the drawing, there are like two different clusters which have collective links. So there are two sets of collective links that end up being in the same cone.
Mhm.
That's the first point. Could you give an example of that? I know examples are troubling, but something that is a cone of two different sets.
Yeah, I was thinking about this because I knew this is like,
Sorry.
okay, I give you some ideas, but they're very like not concrete. Again, it's hard to construct this in a concrete way, but there are many examples in the book where they do this, I think. But from my intuitive sense, or my intuitive way of thinking of it, in the United States, there was this, insurrection thing that happened, right? There's a bunch of people like took over Congress building, and there's basically two ways of looking at it. Either it was like an act of like a coup, an attempted coup on the country, or it was trying to take back the country from those who had already stolen the country away, right? Either it was legitimate or illegitimate. And it basically, I think this kind of happens in any type of, if you like overthrow the government or whatever, there's like two ways of decomposing that. Was this a legitimate or illegitimate move, right? And really legally, it's kind of impossible to say, because you're trying to take over the very mechanism that makes the laws. So of course the laws themselves cannot really cover this, right? This is also kind of touched on by Carl Schmitt in his work on politics, right? So this would be an example of a multiplicity principle, which is like the transfer of power in a country. The kind of not just that, but like almost any kind of radical shift in a nation, right? Is it legitimate or is it not? Is it covered by the law or is it not? That's one example. I don't know. Does that make sense?
I think it makes sense, but it's I think the problem is maybe that the object is hard to picture in a sense, but I do think it helps out a bit.
Yeah, and conceiving of an event as an object is, I think, a little trickier, but I think it also, has a pattern underlying it, which is not only the things that happen in the event itself, like people, stormed the gates or whatever, broke in. Those are part of the pattern, maybe, but also the larger context of what was happening before and after may be relevant. Another example I was thinking of is like, certain works of art are complex in the sense of the multiplicity principle, because you can have different readings of that artwork. And when you read a work of art in a particular way, you're highlighting certain patterns, right? Certain things matter for that work of art more than other things. So it's like you're exactly what we were showing with the highlight. There's a whole mass of relationships, a bunch of fuzzy space of the artwork. And when you're doing a reading of it, you're highlighting specific relationships that you think matter.
Yeah, that's a good
Yeah.
That's a good example. I was thinking about a poem because, for example, you have a set of an order of words, and they are words, so they are in a sense a combination of sound and sense. And you can read the poem simply as a connection of sense, like this and this and this and this. But you can also read the poem as a structure of sound, from rhymes and rhythm, etc. And these two sets of form, these two sets of reading, they're not completely composable in the sense that you can't map one into the other. Maybe I'm thinking too much, but I think there's, is that some kind of degenerate object?
Yeah, exactly.
So I could
That's
say a
degenerate.
poem is a degenerate object. This is good also for my anti-poetry shtick. It's good for this, so I'll be able to say that. I mean, okay, thanks, Dennis. You've helped me out a lot in many senses.
Yeah.
So this is also a degenerate understanding of what you're saying.
Yeah, we all have, from this presentation, probably a degenerate understanding of this material. Yeah, exactly what you're saying. Like if there's two ways you can decompose an object such that those two ways don't have a mapping between them, like they're just kind of in a non-relational way towards each other, then you've hit upon something with the multiplicity condition.
You can still establish simple connections with different patterns of the same cluster, right? I mean, for example, you can do just a analysis of the sound of poems and then compare those sounds to other sounds. I mean, sure, those are kind of more simple comparisons, but if you compare sounds and then you compare meaning and then try to compare those two things, they won't like just match up, right? Something like that.
Yeah. Yes. So taking this whole diagram into consideration, maybe the first purple line is like meaning to meaning. The second purple line is sound to sound. And then you have this issue of the link that these two form. Yeah,
though here we might fall into that problem, which is we don't want you, again, we did the qualitative thing where what is the common ground between discussing sound and discussing sense, right? I mean, perhaps there's a way of talking about information that would make this kind of a flatter kind of duality of patterns, right? But it's a very charged example because it already kind of hints at a very different quality. Then it's kind of obvious that you won't be able to match these things up. Right.
I think that, yeah, I understand what you're saying, but I think but of course it would take work to point out the homogeneity that allows this distinction. I get what you're saying.
Yeah, I'm just trying to be the annoying person that, I mean, it makes total sense to me. And I think that we'd have an intuition in which, let's say I'm making a comparison of the information contained in like the sound patterns of the poem. Like this is similar to that, this is similar to this, and so on. Then I'm making a kind of analysis of the information and the meaning. This image is similar to that image, and so on. So you could imagine perhaps a way of really reducing this distinction to like the connection between parts of the poem, right? But I would, just try to keep that in mind, because I think, I mean, even our own examples are better in that way. Like I tried to add one here in the chat. I'm not sure if it's perfect, but like you can just imagine like a workplace. People are establishing productive relations, meaning this person relates to that person in terms of I work on this, you work on that, and so on. You can have like communal patterns, like this person is a friend to that person, and so on, right? They're all kind of social relations. So they are, mode A, mode B, and mode C can be treated as types of patterns, even though they're all kind of homogeneous. They're all social patterns, right?
Yeah, this is something that I was thinking now that you said it, like if since the different types of modes that we have developed, they are distinguished in very simple terms, not needing extensive definition in like something that it has to be a certain knowledge or a qualitative distinction, in a sense, they could be thought of as the degenerate, like a social action. It can be treated as a degenerate object in the sense that you can have a cone that is decomposable through these different types of trade intercourses.
Yeah.
I mean, and I think that makes a lot of sense because, and it actually highlights a lot of the problems in the intermingling of actions.
Mm-hmm.
Dennis, does it have to break down into two? Or is it two or more?
Two or more, yeah.
Okay.
At least two, yeah. Yeah, but yeah, this thing about the qualitative jump, I mean, I think here, yeah, we'll. This whole chapter on relations is like assuming that all relations are kind of homogeneous, but yeah, but it is not. Yeah, the more abstract you get with the type of arrow you're using, the more let's say, the more confusing it becomes.
Yeah, but I mean, also the reason why I think it's worth emphasizing this homogeneity principle is because I think so much of what we're doing is actually managing to keep to this, right? I mean, we're trying to construct a lot of different properties of social systems out of the composition of three very basic types of interchange, all of them definable in very similar ways with very small, like just a logical difference, right?
That's true, yeah.
So we are trying to be very constructivist about this and not accept properties we didn't derive from this so-called transcendental logics, right?
Mm-hmm. Yeah. When you apply this construction, you should do that. Yeah, you should definitely choose a specific type of arrow and stick to that.
Yeah, because sometimes this might, if you don't, you might actually lose the emergence of something, right? Mm-hmm. Because the emergence is precisely something you get without having put it in before. So if you think you've put something in, like a qualitative distinction, you will find it evident if you got it out on the other side. Yeah. It's much more surprising when you didn't put it in, things were more homogeneous than that, and then you get a heterogeneous result, right?
Yeah. Actually, what you said just reminded me of an example that I think would adhere to this principle and also be very useful, which is in the relation between laws, because laws have to be adjudicated on in some cases, right? So like a law doesn't prescribe how it doesn't prescribe the cases that it applies to. So we can think of the multiplicity principle in the legal sense as a law that has two different readings. And then the arrows correspond to the relationship between laws, right? So like one law can invoke another law as precedent, or maybe a case as precedent. So maybe there's something there that we could consider, right? So the complexity or the emergence that happens within the legal world, it happens because the same law can be read in different ways, and therefore not always, it's not clear. You need that work of figuring out how to apply the law, which is not given.
Yeah. One thing that I like a lot about this approach, I think we've spoke of this before, is that I find that, at least kind of in common sense, we associate complexity with dynamism, right? If something is dynamic, it's messy, or it interacts in many ways across time, that's kind of a fundamental condition for thinking about complexity in some way. And I just like in common sense, and I find that this kind of very relational, but also it's we haven't introduced, these arrows don't need to mean that one simple link happened in time, then the other simple link happened, and then you're composing moments in time, right? I mean, it's a more structural account of complexity, I think, that then you move into like, okay, how does this play out in time? You don't need to assume like a temporal unfolding before and then discuss it. So it seems like it's neither like a more classic informational account of complexity, just like if there is kind of irreducible information in the whole that is not in the parts, right? And it's not like a dynamic account of complexity where you just get the sort of interaction and then in time some stability of a higher property appears. It's more structural than that, I feel like.
Yeah, definitely. I'm thinking of this, everything I've presented so far, I'm thinking of it as it's the synchronic part of the structure, and the diachronic, or the one that moves through time, is coming up. And yeah, and then the very interesting thing is how those two things interact, because they have a very good theory, I think, that ties the two aspects.
I really like your legal example, Dennis, the more I'm thinking about it, because it also, I think, kind of gives a useful intuition to like the directionality of the graph, because in legal reasoning, you have to you have to follow from more fundamental, like constitutional principles in a direction towards like your actual interpretation in any given sentencing or decision or whatever. And it's a very like tedious, kind of really dry, boring thing. And it's a really good way to kind of capture how actual kind of like places where we could kind of historically or politically say that there are antagonisms or whatever, say like in the history of the United States and its constitution, like how those can manifest while also being kind of like just dry informational problems, right? Because there's a reason that, say, like the current like ending of abortion rights, like there are actual semantic reference for that in the Constitution. That's not just some bullshit. Like that's not bad jurisprudence. That's the problem, right? Like there's actual like reasoning to get there. But there's also, and this is what the decisions don't really acknowledge, is that there's also a reasoning from Roe v. Wade to get there too, right? Like there's
exactly.
There's an actual like, yeah, I think that's a really good way to capture that without kind of like just explaining away judges' decisions by, oh well, they're conservative, therefore that's why they reason that way.
Yeah, exactly. I mean, even if you want to assume they're manipulating the laws, or they're like kind of bending things, I mean, I think everyone does that. Like you want to bend the laws, you want to interpret the laws in such a way to achieve some goal, right? But in order to do that, you have to respect the constraints that the legal texts put forward. Like you can't just start from anywhere. You have to start from what it literally says, and therefore you are basically talking about a category consisting not of people, but consisting of these legal texts, and then the relationship between these legal texts, which it's still kind of nebulous what that arrow is, but I think it's closer to what Gabriel's saying, that it's the same arrow, right? The arrow, the blue arrow here is an arrow between two legal texts. The purple arrows are also those relationships, but they're qualitatively different, right? There's one that's complex, because it's
isn't that where we can kind of go back to Rosen, and a lot of like the arrows are entailment relations, right? And then that's where really like categorification, like in a legal context, entailment is like looking back into earlier case law and seeing what precedents imply for future precedents. But once
Mhm.
like, and that's the thing that's so fascinating about precedent, as like an actual social thing, is like it actually does set into place like an inferential, you know, a new kind of proposition, I guess, inferentially, that then has semantic consequences going forward.
Yes.
And it's quote real, right? Like it's not something that you can easily, like a judge can easily lose their bench if they don't follow that entailment structure seriously, I guess.
Yeah, exactly. Your whole career, is to develop a sense for this, for these arrows. So it is a real thing. That these arrows are the bread and butter of lawyers and judges, that the legal mind. Okay, so multiplicity principle will return later, but I can continue from here. So I said earlier, you can bind patterns, but you can also, let's say, unbind them, or not unbind, but like look at their underlying patterns. You can project them into their underlying patterns. So the categories we were talking about previously, I didn't assume that they were hierarchical, but going forward, it becomes useful to start to talk about hierarchies in categories, and those are basically categories in which every object is assigned a level. And when you look at, like, let's say level 5 object, that means you can decompose it to level 4 and see the underlying pattern below it. But then every object in level 4 can be decomposed into objects of level 3 and so on. So this is what they call a hierarchical category. And it's useful because when we talk about things like scale, which is, it's really important for us in SDP, scaling up things and looking at interactions at different scales, I think we're basically working within a hierarchical category. Right? We're basically trying to understand why certain effects only occur at a certain level, but they may not occur at other levels. So when you take an object and you start to like unfold it, you are creating what they call a ramification. A ramification is just like the same object in different scales. Or it's a procedure where you construct the different scales of an object. So you think of it as like a zooming in operation of the object. And a ramification has a bottom level, right? It's where you stop looking. So you might not need to go all the way to the bottom of the category, whatever that is, right? Which I wrote here, they're called the atoms. You may not need to get to the atoms of the category. You may only want to see like the first 3 levels of unfolding. So that's what we would call like a 3 ramification. If you only see 3 levels. In the picture on the right here, I'm picturing a 4 ramification. So the number before the ramification indicates the number of decompositions that have occurred. This is also really similar to what Renzo presented in his interaction model. I think he also called it like an unfolding, right? And then you have multiple steps, and you basically see the complexity underneath a given object. So I think all the examples that Renzo gave of like, I think divorce is one of them, and like, kind of a protest, right? You can take those examples and kind of map them onto here. Look at the levels. So the bottom of the ramification are called the microcomponents. That really doesn't come up again later in the book. So, but what's important here is that the complexity order is the highest level the ramification, which contains a complex link. So in the drawing on the right, you'll see that level 2, which because at the bottom is called level 0, level 2 has an arrow going from two objects, right? This is the complex link. Because that complex link exists at level 2, we can't reduce it uniquely to the next level. We have to choose a decomposition. But actually, no matter which decomposition we choose, we're not going to capture the whole, the logic of that arrow, right? Similar to what we were just saying about legal entailment, right? You can break it down to the underlying legal text and what they're saying, but because there's this multiplicity principle at play, we cannot reduce the decision to just those texts, right? The pattern, there's no unique pattern that will allow us to explain away that legal decision because of the fundamental ambiguity or fundamental degeneracy in the object. You can't do this reduction procedure successfully. So that's basically how you model complexity, right? You have an object, you unfold it, but the complex links are kind of like the obstacle to that. And you can measure that by the complexity order. The complexity order is basically the level that the unfolding stops being a reduction.
So just understand, ramifications is when you can zoom in, like by unfolding the co-limit, going through its collective links back to the patterns, and you're not losing any information, right? But the complexity level is defined by when I reach certain levels that if I now try to unpack or unfold it to its ramification, I will lose some information. So I'm obliged to, if I want to keep the information, I need to stay at a zoomed out level, for example.
Basically, the ramification ramification is not the same as reduction. So ramification is like one path you took when you zoomed in, but it doesn't explain it. It doesn't necessarily explain everything. You may notice so the ramification here, like it successfully went past the complex link, right? It saw the complex link on level 2, and then it continued to decompose into level 3. The only problem is that level 3 cannot explain the complex link on level 2.
I think a place for this in our theory is in Guittar's monster, the original inspiration for the monster, right? Like you can split off into pairings, which is already cutting out one of the 3 logics, right? So there's like that's the first level where there's a complex link that we kind of like, we choose to go past it if we like look at the world just as like A plus B. And then you could even go down further. You could skip another complex link since A and B are also kind of tied together. But like that's the first place you run into, right? That you kind of like are already cutting a complex link.
Yeah, exactly. I think that's a good example where it's not that you can't go further, but if you go further, you have to make a decision on what's relevant, and you have to accept that not all effects will be explained by that ramification. Right? A ramification is one decomposition, but there could be other ones, I think. And they are not necessarily compatible. Like one ramification may be totally inconsistent with another one.
Mm-hmm. Well, that seems really, and like the micro components versus atoms seems really useful in this context, because like we've looked a lot at like A plus B as an interesting place to explore nationalism and populism, all this stuff, and that would be a micro like you run into things that are still made out of a pairing, so they're not the fundamental kind of logics of A or B or C, but from a certain perspective, that's as far as you need to go to kind of like maneuver or navigate the nationalist populist world or something.
Mhm. Yeah, I don't know if it distinguishes microcomponents to atoms, but they both seem to serve that thing, because by choosing a category, you're already kind of picking your atoms, you're picking the smallest things that matter. But with a ramification, you're doing that again within a category for a given object. Maybe that the microcomponents of an object for a given ramification are different for some other object, and you want to compare those things.
Yeah, that's Violeta asked the same thing I was going to ask. Are all objects of a level the co-limits of patterns of the level below, right?
Yeah, good question. Yeah, yes. Yeah, if you aren't the co-limit of anything, then you're just an atom, I think. Yeah,
Yeah,
and
so,
again,
but
it's a very specific category. These are hierarchical categories only. So there are other categories where obviously this leveling thing would not make any sense, right?
I think at the end of the book, they actually add like some other cases, like after they explained consciousness with all of this, that they have an appendix, and they say you can have local co-limits and multi-co-limits and hyperstructures, and some of these are not hierarchical, I think.
Mm-hmm. Yeah, definitely. We are scratching the surface. We're getting the simple version of the theory.
But in either way, in this particular case, we're actually deriving what we would call a hierarchy from the fact that we're moving. Let's say, if we are able to keep the information of some pattern simply from the relation, simply by looking at its co-limit and its relation to other co-limits, that's, let's say, how we derive a level, right? We're not assuming that there are levels. We're saying that if this happens, then there will be two levels, right?
Yeah.
Because
yeah,
I can.
If there's a
right. Yeah. Okay.
Yeah. If you see a relationship that obeys the commutative rules of another pattern, then you automatically are stratifying it without presupposing that it's not by virtue of the objects themselves that they belong to level whatever.
Mm-hmm.
It's because of their relationships to other objects, and those relationships of those objects to some other objects, right? So relations on relations. Then you can distinguish the levels.
And how do I name the difference between, let's say, I find the co-limit of a pattern, and then I treat it as an object that of a new pattern, and it has a new co-limit, this higher pattern. Then I can distinguish these as levels. Mm-hmm. But then there is also the distinction if let's say the links between these co-limits will be simple links, or some of these will form complex links. This has a property which is now this, let's say, creates an obstacle to this more reductive approach, right? I will not preserve all the information if I just try to analyze it in its ramification, in its unfolding, right? Mm-hmm. So in one case, I produced a level because just co-limits are treated as objects for new patterns. In the second case, where these co-limits are forming complex links, there is no other name for this, right? Irreducible level of some sort. Like, it's not like level versus hierarchy.
Yeah. This level, I mean, they do talk about it in terms of the links. So there's this idea of n simple and n complex. So I'm a bit hazy. I don't remember exactly the definition, but I think it's something like if you're a complex link on level 2, then you're a 2 complex.
You're just too complex.
2 complex, yeah. Like you can also be 3 complex and 4 complex. So it's a way of indexing, because not all complex links are equivalent, right? There can be complex links that arrive late in the game, so to speak. And some complex links are kind of, they emerge early on. Yeah, but these are good questions. I think have to consult the book to know. I try to avoid a lot of terminology because they introduce it like 10 new terms every page, so it's like kind of hard to keep track of. But yeah, I think there's definitely a word for what I think you're saying.
I tried to find it here. Violetta is asking how they define this, the level. What part of it, Violetta? The leveling thing.
Yeah, this definition of like, yeah, the leveling. Like this looks like a well order, like in the sense of in this definition of mathematical of well order. But it looks like it just doesn't feel like this should work categorically, like the definition formally. But I'm not sure if like this is relevant, guys. How formal, how much this actually formally can be written.
Yeah, I think the way they describe it is it's an assignment of a number to every object, such that if one object is a co-limit of another set of objects, then it must have a greater level, right? But yeah, that is not true for most categories that mathematicians study. That's a very specific case. So I don't know, maybe the reason why is because it's not really useful in mathematics.
Yeah, it's actually really interesting definition. Like I would be curious to know what categories satisfy that.
Yeah, I mean, these are categories that, like a category of a social system or category of a workplace, like if you consider, low-level employees and then their managers and then the managers of the managers and so on, like that's, in some sense, we can talk about that as a category, but it's not, mathematically very specified.
Yeah, I mean, they call this what they call hierarchical categories, right? But I don't remember which. I'm trying to find here in the actual book. Where we are.
I mean, yeah, I was thinking in math, wouldn't if you took like the number line, just take like the integers and subsets of the integers would all have a upper bound, right? So wouldn't the upper bound be the co-limit?
But I'm not sure that's what she asked if has a mathematical definition, because co-limits are everywhere. I think the point is this iterated co-limit thing, right? With that complex link property, right?
Yeah, no, but I'm saying that is an example of one where you can partition every object because it's totally ordered. So
yeah, I think any well order or any total order, like I feel like orders are just gonna naturally work for that, like because orders make a category. So and co-limits are like upper bounds. So I think like, yeah, I think that example is probably gonna work. But I guess the interesting thing would be other things other than that.
Yeah, other things. Yeah, then it's like you're
Yeah, those
kind
are
of,
like I think the most natural examples. But yeah, I think you're right. I have to write it down.
mhm. Yeah. So yeah, this is a very particular case that they find it useful also because they're trying to study like biological systems and how they become. They want a concept of things becoming more complex over time, so they need this idea.
Yeah,
Which
the examples they give at the end of this chapter are some geopolitical stuff, crystals and quasi-crystals in chemistry, and multifold objects,
mhm.
which I don't know what type of thing that is.
Yeah, they choose the. I like their examples; they're pretty nice, but they choose some out there examples, I think. Okay, so I'm gonna go to the next slide. I think it's already been 2 hours. I don't know. Should we continue here or?
It's up. I think it's also up to you, man. Like, I'm not sure if what you have planned for the other meetings, if we should stop and just have a general discussion after a small break. Like, what do you think fits your?
Yeah, I have only like three or four more slides, so I can finish real quick, and then depending on what everyone is interested in, I would steer the next meeting towards that part of it, because I think with the remaining slides, I pretty much cover everything up to the co-regulators, and then there's still the whole concept of memory that I'm not covering at all in this meeting. And then I also wanted us to talk about how it applies to SDP and like the comments that John brought up also, like with the monster diagram, how we can use this. But yeah, let me just finish because I think the next parts are interesting anyway. And we have a good momentum. Okay, so yeah, we have these hierarchical categories, and in category theory, there's this concept of a functor, which is a map that preserves composition between two categories. So again, you have these arrows and objects within a category. Now we're taking those arrows and objects of category 1, and we're mapping them onto arrows and objects of category 2, such that if you were to compose 2 arrows in the first, and obviously if you compose 2 arrows in the first category, you get a third arrow, right? That third arrow must also be mapped to the composition of where the 2 constituent arrows were mapped to, if that makes sense. Basically, yeah, we've talked about this before, but it's like that composition operator needs to be respected. And the innovative or interesting thing that they do with that is they try to model time as a sequence of functors that technically they're partial functors because not the entire category is mapped necessarily, because they want to allow for some objects to disappear, right? The rule of any mapping in general is that every element of the domain must have a corresponding element in the codomain. But for them, they want the possibility that some elements, some objects in the source category don't have a corresponding one in the next category, which indicates that they've kind of died off, right? They disappeared. Okay, but that's a side note. Here we're trying to add dynamics to our category, to our system. So previously we've looked at it as the synchronic view, right? This is in one instant of time. What are the relationships and how do they compose? How is a body composed or of its organs, of its cells, and so on at a single moment in time? Now we're trying to push that through time and see how the different components of this body are changing. So here, every category becomes a slice or an instant of time. And yeah, you get all these new properties that appear by doing this. So one property that is interesting is the idea of a propagation time. So if you imagine like the objects in one category, they're being assigned to another object in another category, right? So if that is the passage of time, then the assignment of this object represents like that object in the future, right? And going forward in time. So instead of we're talking about an instant of an object, we're talking about the collection of objects, one for every category that are mapped in succession, right? Basically, the picture here makes sense. Now, there are some links between objects that take time to establish. Like, I have a relationship to you, but that relationship is not happening in an instant. It's happening over, for example, like a phone call. If I'm talking to you on the phone, that I'm interacting with you, and that takes some amount of time. It's not an instantaneous relationship. So the propagation time is meant to describe this, and it's basically a composition rule. It says that, and it's not pictured here, but imagine there's like a time scale at the bottom that tells you the length of time that has elapsed. It says that I cannot create a composed arrow that goes horizontally unless I have exceeded the propagation time of the link. So imagine that every link that an object has with any other object has a number associated. That number is the propagation time. And and also the horizontal arrows in this diagram also have a number. Maybe if I draw it here, it makes more sense. So like, I'm gonna draw some numbers here, right? And then this is time 0, and this is time, I'm gonna draw a number here also. I'm gonna say this is, must be 4, right? So 1, 2, 3, okay. 1, 2, 3, 4. So let's say time 4 is here, or 4 whatever units of time. This link between object A and B takes 4 units of time to happen, meaning that this arrow here, it cannot have a composition from here to here because this is under 4 units, right? If this is happening at this point, the elapsed time has not occurred yet. Only when we're at this category, which is after 4 units of time, can this diagonal line be established. So then the question is, okay, what is this middle arrow here? You said that I said that this interaction is not happening yet, right? This is let's say the partial interaction. So maybe if I'm dialing a phone, this is like the moment before you picked up the phone. And then once you picked up the phone, the interaction has established itself. Something like that, right? So there's a delay or a propagation time that is required to pass before this original link can be fully established. And when it's established, we have this diagonal arrow here. Okay, so all that is just to say that there is a kind of a rigorous notion of something unfolding in time, and not not having an instantaneous relationship to between different components of the system. This is also really interesting for us. So they have a concept of a strategy, which is basically what a functor accomplishes. Another thing about this picture is in between T1 and T2, I'll draw here again. If this is T1 and T2, there can possibly be many categories in between here, right? I just don't picture it, but we want to think of this as just like a continuous cylinder, let's say, and you can slice it in many different ways, but it can be can have a thickness to it. Okay. So a strategy is basically how you want your system to evolve over time. Your system can gain objects or lose objects. When it gains an object, we call that absorption, or it can be absorption. And that's when a pattern that doesn't currently exist in the category now exists in the category. It can eliminate things. So some objects and links are discarded or removed in the next category. And then you can bind something. So that's when an object takes the role of the co-limit of a previously given pattern. If you combine all three of these possibilities together, you get a strategy. The language is intentionally evoked as something that the system is trying to achieve. Obviously, that doesn't have to be the case. It can be accidental that one object that becomes the co-limit of a bunch of things. It doesn't. But the reason they choose the word strategy, I think, is because you're evolving the system in a way that obeys some goals. Here, I'm trying to think of I'm trying to call back to like the discussion with Rosen and Rosen's distinction between mechanical systems and living systems. Living systems have this kind of anticipatory aspect to them, where it's not simply about the previous state causing the next state, right? But rather there's this kind of the final cause in Aristotle's four causes. There's something that is built into the very purpose of the system that drives it forward. Something like purpose, something like intention, or a form of life to the system. So the idea of a strategy is really how the system achieves some kind of aim, right? The system is trying to become complex enough for some particular purpose. Maybe it is just to survive, but still, yeah. So here, a complexification with respect to strategy is the configuration category after you apply the functor, which is specified by the strategy. So these three boxes, these colored boxes, are the strategy. What the first box says is that I want to absorb this this pattern. So if you see on the left-hand side, we have a category with 4 objects unconnected. In the next iteration, we have 2 objects that go to the same one, which is basically the pattern in this bluish box here. The second box says, I want an object to now be the co-limit of 2 of the previous objects. So I've added a co-limit in the next one. And then the third box, the red one, says I want to remove these 2 objects. So yeah, that 2 of these objects were removed. Right. So here the strategy are these 3 boxes together, kind of similar to the sketch, right? The sketch is like an abstract graph, but then it's implemented into a category. So the strategy is like a sketch. It's like a abstract set of requirements. And the complexification is like the implementation of that strategy into the system.
I don't think I understood the strategy bit. I mean, is it I'm sorry if, but is it like something that is preordained? Is it there's a finality, and then these actions are what it means to fulfill the strategy? I think I might have missed something.
Yeah, it's suggestive language that is applicable to like certain systems, but they also have a problem with this term strategy. They say like maybe they changed it actually in the book. I think they call it option, but I didn't like that term. Yeah, but it's not necessarily preordained, right? You can think of a system as just kind of chaotically moving towards whatever, right? Just evolving according to some random process. And then therefore in that case, the word strategy doesn't really make sense. It doesn't have a strategy. It's just like chaotic.
Mm-hmm.
Yeah, but the term is chosen to describe a more intentional or preordained type of. It's there to evoke it, to allow that to be a possibility.
But I think
Okay,
also it's
so
because, Rafa, it really helps if you just think that if you separate, let's say, if there is something like this strategy being applied here, right? Just imagine that there is some other thing, which is, let's say, any type of agency, intentionality, whatever that is defining the protocol, right? The protocol itself is what's the strategy. Now, if this is the effect of, a previous plan that you're anticipating, if it is just, let's say, some reinforcement that it's regulating, like if this is the case, there's some chemical process that drives this forward. Like it doesn't matter at this level, right? So I think if you just separate the idea of strategy as the kind of settling of a course of action, right? That's why I think they call it option. From, say, what's the purpose of establishing that course of action, right?
So it's simply the set of options that are possible in this from one configuration to the next in the partial functor. I mean, I'm sorry. It's because I think it's a bit it's a lot of information, so I might be confused at this point. Because I understand that we're going from there was the whole first part on the hierarchies, the patterns, etc. And now we are treating them dynamically in the sense that there is the movement inside one structure, right? And
Yeah.
what you are describing, if I understand, is like, okay, so what is the change between one state and the other? And there are three types of changes that can happen. Is that it?
Yeah, and they can be a combination of the three.
Oh yeah, sure. But you can have like, so a strategy is like the types of processes that can happen in this changing configuration.
Exactly.
Okay.
I don't think it's the
Yeah.
space of possible configurations is like the funneling.
Space of possible.
Is one option, is one strategy, right?
Yeah.
Okay,
Yeah, because one possibility is one strategy, but there could be many possibilities, right? There could be many strategies that can make your system go in many different directions. But the one that achieves these three things, you can think of these three boxes as objectives. They're things I want to happen, right? And then a strategy is a thing that makes it happen, that makes the category on the left satisfy the constraints of the three boxes.
Why I don't think, why does it have to satisfy those three?
Because I'm looking for a way to get to a place where these three things are sadified. I as the guy setting up the formal experiment.
Oh no, okay, so it could be any other configuration of combination of forms, or no?
I think that they're just saying that there is the fundamental claim that they build on René Thom, that there are only three possibilities for each part of the system. It can either be absorbed, eliminated, or bound, right? Like there's nothing else can happen. So every strategy will have to be built of these three things.
No, yes, but it doesn't have to have all three at the same time.
Oh yeah, no, it doesn't.
That was my question.
Oh, okay, sorry. Yes, yeah. In that case,
yeah, because I wasn't understanding why. I mean, sorry, it's like a stupid question as always. I wasn't understanding why there were like, okay, you have to fulfill these three. I was trying to understand if it was like three things that you had to fulfill for it to be a strategy, or if you chose. Yeah, like that was my question. I'm sorry.
Yeah, no, I should have shown different strategies. It would have made more sense. But yeah, like this is just one strategy I just randomly, because it looks nice in a picture. But really, I could have had just the green box by itself and had, or just the red box, or red and green, or nothing, right? Nothing is also a valid strategy. Yeah. And for a given strategy, there could technically be different functors, different ways you can achieve that goal, right? It may not have been done in the same way, but basically there are different paths to the same, to satisfy the same strategy. But in the categorical language, all these paths are kind of the same, right? They're equivalent. But I think the reason I was trying to also talk about the thickness of the temporal drawing here is, again, I'm going to do this again. I don't know if it makes sense, but this is actually like infinitely subdividable, right? It's temporally divided, so you can basically take instance within instance to pinpoint the category you care about. A strategy is something that takes time to implement. So it could be that the strategy only gets fulfilled at this very last point here, but it's in the process of finishing in between, right? So there's a propagation time again. The reason this is important is because strategies can be decided by the parts of your system. It's not that I, the person creating this category, am deciding the strategy, because that would be kind of an empty gesture, right? What is happening is that you will have elements in here called components that are persisting through time, and they are the ones that decide the strategy collectively. Here's a little insect that is kind of crawling through time. Okay, I don't know if that's clear, but I think the next slide will make it a little clearer. Okay, so this idea of strategy is just how you fulfill certain objectives in time. The stability question, let's see if can I go to the next one first? I'll go to the next one and then go back. So the co-regulator is a subsystem. This is what I was trying to draw in the previous picture. It's a subsystem of our evolutive system, whose components act together. So each one of these like cylinders is actually like a subcategory. It's a part of the category consisting of many objects. So there's many objects in each of these cylinders, and these objects act together. They're actually called agents. The agents of the co-regulator, they have their own model of the world. They take in information and they build a kind of a state internally about the outside. And this is called the landscape. And they can perform operations, like they can talk to each other, basically. So these arrows here is the co-regulator 1 talking to co-regulator 2. And then you can see at every slice of time, a different interaction is happening between them. Okay, and the reason I jumped to this slide is I'm trying to say that the strategy which moves the entire system forward can be the outcome of this interaction between the co-regulators. And I think that's why the term strategy is relevant, because it's kind of like saying that these co-regulators are steering the ship. The ship is the entire category. The co-regulators are just the small parts of it that are acting in some coordinated way. They're working together, and they're able to make, in some sense, make decisions so that the end result will satisfy some strategy. Here's an example, like if you cut yourself, your body is healing that cut, assuming the cut is not too bad, right? Your cells will replace the damaged cells over a long period of time. That's a strategy, right? On the one hand, it removes dead cells, right? Your body is to remove cells that were damaged. So that would be the elimination step. The binding step would be creating new tissue to cover over the cut. And absorption maybe is like a pattern. I don't know if absorption happens actually. Maybe absorption is like the nutrients that are necessary for carrying out the activity, right? So this is happening over time. And the co-regulators here are the cells that are communicating or working together to achieve that healing. Again, I think actually I didn't even finish the last slide, so I'll stop at co-regulators. I'll go back one more and talk about stability is an interesting concept. So we said before that an object can be a co-limit for a pattern. The stability of that object is measured by how long it is the co-limit of the same pattern. If the pattern changes, that is an unstable event, so it stops the stability span. But as long as there's a core pattern, which I've drawn here as the red circle, that is the core pattern. Everything in the green here can change as long as this object is still the co-limit of this red pattern. And again, this outer pattern can also be like have collective links to this co-limit, but it's allowed to change. But this red one should not change, right? And the length of time that this red pattern stays the same measures the stability of this object. Okay, that's everything in the presentation. Yeah. Oh, did you have another question?
Yeah, no, actually, it was like I first I wanted to thank you. I mean, I'm really happy to have been able to follow your presentation. I thought you were very pedagogical, and I think everything was very clear to me. But I do think that some of the interesting parts in the end, like when talking about the strategy, the co-regulators, I think maybe because of the time, at least for me, I wasn't able to absorb it so much. So I was wondering, because you asked if what we could talk about, I was wondering if in the next presentation, maybe you could begin from that part, because I think there's a lot of stuff that will be useful, and maybe with a fresher brain, I'll be able to follow more closely, because I do think that you're really latching onto something that is very, I mean, it's very helpful to structure certain things in a more precise way. So I was wondering, I think it's something that you could start, like when you do your next presentation on this series, I think it maybe could be a point to start, like just from the diachronic, like when you move away from the synchronic part of the presentation.
Mm-hmm.
Yeah, I agree.
It's a good idea. Yeah, I think
I feel like
that's what I'll do.
Yeah, like for example, I remember in the book, they give specific examples of, let's say, strategies that, you know, end up simplifying the categories, strategies that actually complexify it, because it's not necessary that patterns that didn't have co-limits will not acquire co-limits, right? Things like that. So I feel like that's something I would like to understand a bit better. I mean, the co-regulators part, it just seems like we don't know what it means for like objects in this slice to be like form a subcategory, and what does it mean that they are kind of to be thought together. It's not the same as a distinction of levels, right? It's a more functional distinction, right? So I get lost a bit there. It just seems like there's a lot of implied stuff. So I don't know, I agree with Rafael that probably if we just divided the more synchronous point of view today, and then the more diachronic point of view, and I mean, going a bit further, you know, it would be a good kind of criteria.
Yeah. Okay. So meeting number 2 will be diachronic stuff.
The diachronic stuff.
The diachronic stuff. Yeah, exactly. And I think that will take a whole meeting, and then maybe at the end we can talk about memory, because that's also the other part of the book that maybe I can fit it into just meeting number 2.
Yeah, but I mean, you did kind of put like separate 3 meetings, and if you want to use a tree, we have time to do it, you know. I also feel like there is, like, for example, I can feel a slight difference between the enchainment of ideas in the beginning, which were one idea accumulates on the other, and at the end I feel like they were more listed than enchained, in the sense that there is this and also that, but it's harder to build one from the other, like you did in the beginning, you know. So even if we don't cover that much, but we cover it in the way that you were covering it, you know, most of the presentation, I think it's fine to separate it into 3 meetings, and even if we leave a larger chunk of the meeting to just speculate on top of it or go over details, you know.
I also think that since these are such technical tools, I think it's good to take our time. I mean, if it's not too much for you, but I think taking up the 3 meetings, but going over this stuff like in a way that we can not only like understand theoretically, but be able to, because I think, like Gabriel said, I think the first part, I was able to understand it like rationally, let me say. The second part, I mean, I could take it more like in images or in metaphors. And I think, but I do think it's something that's very worthwhile. I'll definitely be looking up the book to not understand any of it.
Yeah.
But I loved your chewing it up so it can be tasted. So
I think the reason the second half of the presentation is going to be like less digestible is because I myself have trouble with it. Like, it's the co-regulator stuff, and it makes more intuitive sense on some level. It's more practical, right? I can think, because we've been talking about, you know, Badu and organs and the kind of this, we're trying to do this more dynamic picture of interactions. Also with Renzo's presentation, we've been moving in this direction. So it seems like this is the right formalism for that. But I think it starts to get harder because there's less examples that are at least easy to describe. Right, we have to actually start looking at history, I think, in social situations, social worlds.
Yeah, I don't know. I think I have the impression that, especially using, like, it might take a bit of fine tuning, but a lot of what Rodrigo introduces in his book in terms of leadership functions, organizational cores, vanguard functions, those things, I think they have useful counterparts here. Like they are kind of already network-like concepts. They imply like complexification, changes of kind of levels and things like this. I think we could kind of try to use some time. We can even meet outside of our Monday meetings to try to work this out, because there is something more intuitive in his ideas. So, and they would provide examples that are already closer to our own work. So working in that direction probably would, you know, mutually clarify the two things.
Yeah, it's a good point. Yeah, the definitely the connections with Rodrigo's book that's one of the main references here. Like the whole thing with diffuse control, I think could be modeled as using co-regulators.
Mm-hmm. Yeah, man, but this was really, really amazing.
Yeah, thank you all for sticking with me. Now, this is one of the longest meetings, at least recent meetings.
I can see this really tying a lot of things together for us, and like, yeah.
Yeah, I think also it's one of the first times I felt like category theory was not like all formalism, and like usually when we talk about category theory in our meetings, it feels like you have to do so much work to get a little bit of insights relevant to us. I feel like this one, memory evolutive systems, seems to give you a lot more practical consequences for less technical work. I don't know if that's just a illusion from reading it over and over, but it seems like it's like more dense with stuff that's applicable to us.
Yeah, I think so too.
I think that's the thing, is like so much, like there's this weird balance, I think, that came up earlier in the question of like what kind of category it is, of like there's a huge universe of categories that are really interesting in their own right mathematically, but don't necessarily like apply. And in some sense, like the starting point for this stuff might be kind of like mathematically uninteresting.
Mm-hmm.
And like the way it's developed is very, very like socially, historically interesting, and kind of turns around and becomes mathematically interesting once you build it all up. But there might be something kind of like boring or whatnot about like the very first moves that make it kind of like a place that hasn't really been explored, or at least hasn't been the focus of a lot of the more cutting edge stuff that comes out in category theory right now.
Yeah, I think you see that with in the applied category theory community, they don't really talk about this book very much. Even though it kind of seems like it would be, it's the same concerns that community is all about, but yeah, they don't interact with this book, I think, because of what you're saying, John, that it's like mathematically it's not as interesting. It seems to draw more from like taking the language of category theory and applying it to a very like narrow set of concerns.
Yeah,
I don't know why actually. But.
Yeah, no, I was talking to Vinicius about this, and actually, I think we mentioned this some other time, that I feel like this is a problem we have in many different types of interdisciplinary exchanges in our group, which is it's not uncommon that something which actually gives you kind of non-trivial insights on one side of the kind of connection actually sounds ridiculously trivial on the other side. So, for example, politically, we usually have such few tools to talk about, you know, complexity and kind of less substantive ideas of how to build nested structures and things like this, that even like quite trivial ideas in mathematics, if you restrict yourself just to, you know, trying to produce insights for political thinking, sometimes things that for mathematicians sound absolutely like ridiculous, of no interest, if you just take this detour as a way to produce a new insight for people in politics, suddenly it's very useful, you know. And the inverse as well. Sometimes I feel like this happens with the applied category theory folks as well, where they seem so amazed that you can talk about social complexity with this crazy thing, but what they are actually saying politically is like absolutely trivial and kind of stupid, like like Hayek stuff, you know. Like, what if we just, you know, self-regulate through this crazy trend? Yeah, but what you're ultimately describing is like politically meaningless, you know. So it's I find it's that idea of like controlled analogies, in the sense that you want your analogies with other fields to have as many corresponding statements between the two as possible. If they have infinitely many corresponding points, it's kind of you're actually modeling. But even if you're not finding infinite correspondences between like a political system and a formal system, to look for as many connections as possible, what's likely to happen is that, for example, the level of rigorous enchainment of propositions in a mathematical theory will oblige us to explore propositions in our political system that we wouldn't have arrived just by kind of intuitively thinking about it, right? So sometimes that's enough, even if from the mathematical point of view, it sounds like one thing would follow from the other quite obviously, you know. I feel like this book has a bit of this feeling, like you move along the chapters and I have the impression that most of this is covered like in the first couple of chapters in most category textbooks. But if you were to try to develop those ideas without this kind of formal clutch, they probably wouldn't have appeared in that way. And from that point of view of like insights into how to approach biology, social systems, and so on, it doesn't sound trivial at all, right? So it's a weird thing, I think, how these things can go together.
Yeah, I think so. I think the mathematical constraints they always produce new ideas because they are so specific. I think a good example of that would be the propagation time stuff here, that we know things take time, but then being able to formulate that as a law of composition, I think it's kind of profound. Like,
yeah, they derive like a Bergsonian and kind of chronological time distinction out of just like composing these things together, and the limits to this composition and so on, right?
Yeah.
But I find that at some point we should stop and actually work through this kind of basic ethics of this sort of connections we make. Not only because I feel like there is a nice kind of gradient, you know, going from the cheapest analogies, this is like that in that other field, and you learn nothing, but it just sounds cool, to kind of intermediate analogies where it's not true that everything, you're not really modeling anything with anything. Like, it's not true that you can prove that for every meaningful statement in a political or a social system, you can kind of encode it into a formal statement and derive, whatever you derive in that formal system will have a meaningful interpretation, you know, in your social system. You cannot prove that for every proposition, but for a meaningful finite amount of them, you can still come up with something that when you decode from the formal system, you say, fuck, I wouldn't have arrived at this, you know? It's more than an enlightening metaphor, because you're actually using some level of the actual constraints of the formal kind of counterpart, like that there are strict ways of operating that formal system. This is relevant, right? It's not just a metaphor. Like, it's not like when you make a metaphor and you say Juliet is like the sun. Well, but you won't say that it's, you know, going into fusion and will become like a white dwarf. You're not implying any of that about Juliet at some point, right? You want to be able to extract, infer new statements, but you might not be able to prove that all inferences will be also valid, right? So there's this middle ground where analogies are more robust. And on the other side, you have actual modeling where you can actually prove that every statement will be valid, right? But there is kind of a weird specter from like pure empty analogy where you really don't care. You're just making like empty statements between two fields. This middle ground where you can find some pragmatic usefulness, and the more you respect the other fields, operators and forms of rigor, the greater the chance that a new proposition will be produced in the field they are interested in, you know, all the way to the modeling thing. So there is something there that I find it's a useful thing to talk about, because I think it cuts both ways in this connection between formal and social ideas. And it's not obvious, you know, sometimes how to regulate this and how far to push it and things like that.
Yeah, it's very difficult. I mean, we've seen that basically with like trying to get more mathematicians to
try
to interact more with the math community, but we haven't been successful, right?
Yeah, I think we have, in a way, like the amount of mathematically minded people in the group is growing. Matteo, who is you know, working with the applied category theory community, he's coming over to talk in a couple of weeks. So something good is happening, but I do think that without like a good kind of hierarchy, like a good theory of this hierarchy of analogies and so on, it's hard even to take advantage of this, you know. A lot of people's kind of just, how would I say, like, you know, process of losing a bit of inhibition and being okay with, you know, having moved from the emptiest of analogies to something a bit better, you know, like this small progress in learning and feeling more acquainted with it. Like this is a gradual thing. It's not like somebody will one day to another with no training, just through kind of these interdisciplinary conversations, move from politics and philosophy to like become a mathematician, you know. But you can be you can have a nice kind of ethics of how to approach this different translations, I guess. Which I think it's what we're doing. So I know, and I think it's a nice thing to think about. Ultimately,
Yeah.
I think it's crucial also for people who join the group from different kind of walks of life to feel like their, you know, specific kind of area of expertise is being respected, even if it's being kind of put to weird uses, because there's definitely an interest in being aware of and respecting the more we can the particular ways that things function in their own autonomous fields, right?
Yeah.
The inverse
think-
is also true. Like somebody who's like just a militant might be kind of equally concerned, like, okay, but politics doesn't work like this. Are you trying to tell me what I should be, you know, invested in? And that's also not the case, right?
Yeah, I agree. I think in the end, like everyone respects a well-posed question. So like mathematicians like it. I think anybody, if you pose it in a way that's like captures that fields, because like right now we're still in the middle of it, so we haven't seen the upshot of it all. But I think once we really grasp this formalism in particular, and then we're able to translate work that we've done in other presentations, if we translate it into this language, then we can basically pose new problems in this language that I think other people can be interested in.
Yeah.
Yeah, I would be down to dedicate a meeting like in Monday towards this, like stitching together this stuff with Rodrigo's work. Because I think that it's a really good place to like actually test out what it would mean to kind of like develop these theories, but also give space for people to participate in a way that's kind of respecting their different fields and backgrounds. Because I mean, really, it seems like a lot of the stipulations of his book is really like that ecological hypothesis really requires like coming up with conditions for quite a bit of organizational diversity.
Yeah, organizational diversity, and then like the question of how do we think about like antagonism and stability and instability. I think it's all I mean, this formalism allows us to ask those questions.
Yeah. Man, it was really, really cool.
Thank you all.
Thanks a lot, Dennis. This was great.
See you all.
All right. Talk to you later.
Talk to you later.